Welcome to Dreamlab Knowledge, dear listener, where the cosmos whispers its ancient secrets and every distant star becomes a doorway into profound mystery. Tonight, we invite you to drift with us through the darkness between galaxies, to float among phenomena that defy explanation, to witness the universe in all its incomprehensible grandeur. Let your breathing slow. Allow your thoughts to expand beyond the boundaries of everyday awareness, and join us as we explore the deepest enigmas woven into the fabric of existence itself. Mysteries of the universe. Picture yourself suspended in the velvet emptiness of space. Around you, in every direction, stretches an ocean of darkness so vast that light itself takes billions of years to cross it. Within this cosmic sea drift islands of brilliance, galaxies spinning in the void, each one home to hundreds of billions of stars, each star perhaps attended by worlds we can only imagine, and threading through it all, invisible yet omnipresent, are forces and substances that shape reality itself, yet remain forever beyond our direct perception. This is our universe, a realm where time bends, where matter disappears into points of infinite density, where particles exist in multiple states simultaneously until observed, where entire alternate realities may branch away with every quantum decision. It is a place of profound beauty and equally profound mystery, where each discovery seems only to illuminate how much more remains hidden in shadow. Tonight, we journey into these shadows. We will explore the invisible scaffolding that holds galaxies together, the enigmatic force accelerating the universe's expansion, the violent collapsed stars that create ripples in space-time itself, and the strange signals arriving from the depths of the cosmos. We will peer into the possibility of other universes layered alongside our own, and wonder at worlds orbiting distant suns, where liquid water might pool beneath alien skies. So settle deeply into comfort. Release the day's concerns. Allow yourself to become small beneath the immensity of cosmic time and space, and simultaneously recognize that you are made of stardust, that the atoms in your body were forged in the nuclear furnaces of dying stars, scattered across space, and eventually gathered here on this small blue world to contemplate the very universe that created them. Let us begin this journey together into the beautiful, bewildering mysteries of everything that is, the invisible universe. Imagine you are standing in a darkened room. You can sense walls around you, feel the boundaries of the space, but you cannot see them. You reach out and touch furniture, confirm the existence of objects, yet the vast majority of the room remains invisible to you in the darkness. This, in many ways, describes our relationship with the universe itself. Everything we can see, every star burning across the night sky, every galaxy captured by our most powerful telescopes, every planet, asteroid, cloud of gas, and grain of cosmic dust, all of this visible matter accounts for less than 5% of the total content of the universe. The remaining 95% exists in forms we cannot directly observe, cannot touch, cannot illuminate with any wavelength of light. We know these invisible components exist only through their gravitational effects on the matter we can see, through the way galaxies spin too fast to hold together by visible matter alone, through the accelerating expansion of space itself. Scientists call these mysterious substances dark matter and dark energy, names that acknowledge our profound ignorance even as they gesture toward understanding. Dark matter appears to be the cosmic glue holding galaxies together, an invisible scaffolding upon which all visible structure in the universe is built. Dark energy, stranger still, seems to be a property of space itself, causing the universe to expand at an ever-increasing rate, ultimately determining the cosmos's final fate. Let us begin with dark matter, this ghostly presence that permeates the universe. In the 1930s, Swiss astronomer Fritz Zwicky observed something peculiar about the Coma cluster, a collection of over 1,000 galaxies bound together by gravity. The galaxies were moving so rapidly that, by all calculations, they should have flown apart long ago. The visible matter in the cluster simply could not provide enough gravitational force to hold these speeding galaxies together. Zwicky concluded that vast amounts of non-luminous matter must be present, matter that could exert gravitational influence without emitting any light. For decades, this observation remained a curiosity, an anomaly that most astronomers set aside. But in the 1970s, American astronomer Vera Rubin made a discovery that would transform our understanding of the universe. She measured the rotation speeds of galaxies, expecting to find that stars farther from the galactic center would orbit more slowly, just as outer planets in our solar system orbit more slowly than inner ones. Instead, she found that stars at the edges of galaxies move just as rapidly as those near the center. The rotation curve stayed flat rather than falling off as predicted. This observation could mean only one thing. Vast halos of invisible matter must extend far beyond the visible edges of galaxies, providing additional gravitational force to speed up the outer stars. Without this dark matter, galaxies as we know them simply could not exist. Their visible components would have been flung into intergalactic space billions of years ago. We exist, our sun shines, our planet orbits, only because of the gravitational embrace of matter we cannot see. What is this dark matter made of? This question has consumed physicists and astronomers for decades. The most popular hypothesis involves particles called WIMPs, weakly interacting massive particles, theoretical, entities that rarely interact with ordinary matter except through gravity. Imagine a ghost passing through walls, barely noticing the material world. WIMPs would be similar, trillions of them streaming through your body every second, through the Earth itself. Most of them continuing on undisturbed through the cosmos. Massive underground detectors have been built in the hope of catching one of these elusive particles. Deep beneath the Earth's surface, shielded from cosmic rays and other interference, ultra-sensitive instruments wait in the darkness for the rarest of events. A WIMP colliding with an atomic nucleus. Despite decades of searching with increasingly sensitive equipment, including the Lee-X Zeppelin detector, which set new limits in late 2024, no definitive detection has occurred. Some physicists now wonder if we've been looking for the wrong thing entirely. Perhaps dark matter isn't made of particles as we understand them. Recent research has explored the possibility that dark matter might take other forms. Extremely light particles, called axions, or primordial black holes formed in the first moments after the Big Bang, or even modifications to gravity itself that would eliminate the need for dark matter entirely. A provocative theory published in 2024 suggests that what we interpret as dark matter might actually be an artifact of how fundamental forces change over cosmic time. According to this model, if the strength of gravity and other forces varied as the universe aged, we might observe exactly the same galactic rotation curves without needing any dark matter at all. The theory remains controversial, but it illustrates how even our most basic assumptions about the universe may be wrong. And then there is dark energy, even more mysterious than its dark counterpart. While dark matter at least behaves like matter we understand, it clumps together, forms structures, pulls things gravitationally. Dark energy does something utterly alien to our everyday experience. It pushes. It causes space itself to expand at an accelerating rate, counteracting gravity on the largest cosmic scales. The discovery of dark energy came as a shock to astronomers in the late 1990s. Two independent teams were studying distant supernovae, using these stellar explosions as cosmic measuring sticks to map the universe's expansion over time. Most physicists expected to find that the universe's expansion was slowing down, gradually braked by the mutual gravitational attraction of all its matter. Instead, they found the opposite. The expansion was speeding up. This acceleration requires energy, and lots of it. If we add up all the energy contained in normal matter, in dark matter, and in light itself, we still fall drastically short of what's needed. Something else must fill the universe, something that permeates every cubic centimeter of space. Calculations suggest that dark energy makes up roughly 70% of the total energy of the cosmos. What could dark energy be? The simplest explanation involves the cosmological constant, a term that Einstein added to his equations of general relativity. This constant represents a property of space itself, a kind of inherent energy that every point in the vacuum possesses. As the universe expands and more space comes into existence, more of this vacuum energy appears, and the expansion accelerates further. But recent observations from the Dark Energy Spectroscopic Instrument, which has measured light from nearly 15 million galaxies and quasars, hint at something even stranger. The data suggests that dark energy might not be constant at all, but rather evolving and weakening over cosmic time. If this finding holds up to further scrutiny, it would be revolutionary. An evolving dark energy could mean that the universe's ultimate fate is far less certain than we thought. Will the expansion continue accelerating forever, eventually tearing apart galaxies, stars, and even atoms in what cosmologists call the Big Rip? Might the acceleration slow or even reverse? Could the universe someday stop expanding and begin contracting into a big crunch? We don't know. And this not knowing sits at the heart of our cosmic predicament. We have mapped the visible universe in exquisite detail, measured the positions and properties of billions of galaxies, traced the history of cosmic expansion back to fractions of a second after the Big Bang. Yet 95% of the universe remains fundamentally mysterious to us. It's as if we've painstakingly catalogued every book in a vast library while remaining entirely blind to the building that contains them, able to sense its presence only through the way sound echoes off invisible walls. Some researchers have proposed that this dark sector might be even more complex than we imagine. Perhaps dark matter and dark energy interact with each other in ways we haven't detected. Maybe they're different manifestations of the same underlying phenomenon. A few bold theorists have even suggested that dark matter particles decaying into dark energy could explain both the presence of dark matter in galaxies and the accelerating expansion of the universe. Intriguingly, recent research has proposed a connection between dark energy and black holes. Some scientists suggest that matter falling into black holes might not simply vanish, but rather contribute to the vacuum energy of space itself, Measurements show that as the population of black holes grows over cosmic time, the amount of dark energy also appears to increase, hinting at a possible link between these two cosmic mysteries. There's a haunting beauty to this ignorance. We live in a universe where the overwhelming majority of reality remains hidden from us, where our most sophisticated instruments can only hint at the nature of existence itself. Every person who has ever lived, every thought ever thought, every work of art ever created has occurred within that tiny 5% sliver of the universe we can directly perceive. The rest, the vast bulk of reality, flows around and through us, invisible and insubstantial as dreams, yet more real and influential than everything we can see. Echoes from the beginning. If you could travel backward through time, watching the universe reverse its expansion, you would see galaxies drawing closer together, their light shifting from red to blue as they approached. The universe would grow hotter and denser, stars merging back into the gas clouds from which they formed, those clouds compressing into an increasingly uniform fog of primordial elements. Continue backward, and you would reach a moment roughly 13.8 billion years ago when the entire observable universe, everything that would eventually become hundreds of billions of galaxies, was compressed into a region smaller than a single atom. We cannot see that moment directly. For the first 380,000 years of cosmic history, the universe was so hot and dense that photons could not travel freely. Light scattered continuously off charged particles in an opaque plasma, like car headlights struggling through dense fog. No image from those early times could reach us. We are blind to the universe's infancy. But then, at that 380,000 year mark, something transformative happened. The universe expanded and cooled enough for electrons to combine with atomic nuclei, forming the first neutral atoms. Suddenly, photons could travel freely through space. Light was liberated. At that instant, the universe became transparent, and a wash of light spread outward in all directions, a brilliant afterglow of creation itself. That light still fills the universe today. We call it the cosmic microwave background radiation, and it is the most ancient light we can ever hope to observe. Over billions of years of cosmic expansion, these photons have stretched and cooled, shifting from visible light through infrared and radio wavelengths, until now they appear as faint microwaves, corresponding to a temperature just 2.7 degrees above absolute zero, that ultimate cold where even atomic motion nearly ceases. When you turn on an old television not tuned to any station, part of the static you see comes from these photons, messengers from the dawn of time washing over the Earth. The cosmic microwave background is everywhere, coming from every direction in the sky with almost perfect uniformity. It is the ultimate baby picture of the cosmos, a snapshot of the universe as it appeared when it was just 140th of its current age. The uniformity of this ancient light poses a puzzle. Look at 2 points in opposite directions in the sky, as far apart as they can possibly be. The cosmic microwave background from both directions has almost exactly the same temperature, varying by only a few parts per 100,000. How could regions of space that have never been in contact with each other, that were separated by vast distances even at the beginning, have arrived at such precise thermal equilibrium? The solution to this mystery lies in a concept called cosmic inflation, one of the most extraordinary ideas in modern cosmology. The theory proposes that in the first tiny fraction of a second after the Big Bang, we're talking about the time around 1/10 millionth of a trillionth of a trillionth of a trillionth of a second, the universe underwent a period of exponential expansion, far faster than the speed of light. This inflationary period lasted only a minute fraction of a second, but during that time the universe expanded by a factor of at least 1, followed by 30 zeros. Something smaller than an atom inflated to become larger than the observable universe today. It's as if a grain of sand suddenly expanded to become larger than the Milky Way galaxy. This idea sounds fantastical, but it solves multiple problems simultaneously. Before inflation, the entire observable universe was contained in a region small enough that all parts of it could have been in thermal contact, reaching the same temperature. Then inflation stretched this tiny uniform region to become the vast universe we see today. The remarkable uniformity of the cosmic microwave background becomes not a puzzle, but a prediction of the theory. Moreover, inflation explains the origin of all structure in the universe. At quantum scales, even the vacuum of space is never truly empty or perfectly smooth. Quantum fluctuations cause tiny variations in energy and density to spontaneously appear and disappear. During inflation, these microscopic quantum jitters were stretched to cosmic proportions, their tiny variations in density becoming the seeds for all future structure, slight overdensities that would eventually grow under gravity's influence into the cosmic web of galaxies we observe today. When researchers map the cosmic microwave background in detail, as the Planck satellite did with unprecedented precision, they see these ancient density variations imprinted as temperature fluctuations. The map looks mottled, with slightly warmer and cooler regions spread across the sky. These patterns encode tremendous amounts of information about the early universe, its geometry, the relative amounts of matter and energy it contained, how fast it was expanding. Analysis of this delta has allowed cosmologists to determine that our universe is geometrically flat, meaning parallel lines truly stay parallel even over cosmic distances. They've confirmed that the universe consists of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. They've measured the universe's age to within 1%, 13.8 billion years. All this from light that has been traveling toward us since less than 400,000 years after creation. The cosmic microwave background also provides crucial evidence for inflation itself. The theory predicts that during the inflationary epoch, quantum fluctuations in the fabric of spacetime would have generated ripples, primordial gravitational waves spreading through the universe. These waves would leave a distinctive imprint on the polarization of cosmic microwave background photons, a specific pattern called B-mode polarization. Detecting this signature has become something of a holy grail for cosmologists. In 2014, a team using the BICEP 2 telescope in Antarctica announced they had found it, igniting tremendous excitement. The discovery would have been direct evidence for inflation and would have probed physics at energy scales far beyond anything possible in particle accelerators. Unfortunately, subsequent analysis showed the signal was actually coming from dust in our own galaxy, rather than from the primordial universe. The search continues, with new instruments being built specifically to hunt for this elusive signature. What fascinates me most about the cosmic microwave background is how it makes the abstract concrete. Inflation and the Big Bang can seem like pure mathematics, equations on a blackboard divorced from tangible reality. But the cosmic microwave background is real light that you could, in principle, detect with appropriate instruments in your backyard. These photons have been flying through space longer than galaxies have existed, longer than stars have burned. They were ancient when our solar system was born. and they whisper to us still, telling stories of creation in a language we're only beginning to learn to read. This ancient light also reveals something profound about the limits of our knowledge. Beyond the cosmic microwave background lies a darkness we can never penetrate. We cannot see further back than the moment the universe became transparent. Whatever happened in those first 380,000 years, and especially in those first unimaginable fractions of a second, must be inferred indirectly, deduced from the imprints left on the light we can detect. And so we find ourselves in a peculiar position. We can trace cosmic history from the present moment back to when the universe was smaller than a single room. We can describe with reasonable confidence how matter and energy behaved when the entire cosmos was no bigger than our solar system, when it was compressed to densities beyond anything found even in atomic nuclei. But that first moment, that singular instant when time itself began, remains veiled in mystery. The laws of physics as we understand them break down, and we are left with equations that produce infinities. Mathematical screams, indicating that something crucial is missing from our theories. Perhaps one day we will develop a theory of quantum gravity that can describe that first moment, that can marry Einstein's relativity with quantum mechanics and tell us what happened when the universe was born. Until then, we have the cosmic microwave background, a glowing testament to a universe young and simple, before the first stars ignited, before complexity and structure emerge from nearly perfect uniformity. It is our best window into deep time, into the ancient past, when everything that exists today was contained in a space far smaller than what you could hold in your hands. Collapsed stars and twisted spacetime. Imagine pressing an entire star, something like our sun, with a mass 330,000 times that of Earth, down into a sphere 20 kilometers across, about the width of a large city. In this compressed state, a single teaspoon of the star's material would weigh as much as Mount Everest. Every atom has been crushed beyond recognition, electrons forced to merge with protons, leaving only a seething ball of neutrons packed as tightly as matter can possibly be packed without collapsing further still. This is a neutron star, and it represents one of the universe's most extreme states of matter. When massive stars exhaust their nuclear fuel and can no longer resist their own gravity, they undergo catastrophic collapse, their cores compressing in a fraction of a second while their outer layers explode outward as supernovae. What remains at the center, if the original star was massive enough, is an object of such incredible density that it defies intuition. The physics occurring within a neutron star exists at the absolute edge of what we can understand. The pressure and density at the core may be sufficient to squeeze neutrons themselves into their constituent quarks, creating exotic forms of matter that can exist nowhere else in the universe. Some theorists propose that neutron star cores might contain hyperons, baryons, made with strange quarks, or even quark-gluon plasma, a state of matter that briefly existed throughout the universe in the first microseconds after the Big Bang. When these neutron stars spin, they become cosmic lighthouses called pulsars, powerful magnetic fields, 1,000,000 billion times stronger than Earth's, channel radiation out from the star's magnetic poles. As the star rotates, these beams of radiation sweep across space. If one of these beams happens to point toward Earth, we detect regular pulses, some arriving with extraordinary precision, more regular than the most accurate atomic clocks. The fastest known pulsars rotate hundreds of times per second, a nearly incomprehensible rate of spin for objects more massive than our Sun. Just imagine, an object containing more mass than the Sun, compressed to the size of a small city, rotating 700 times each second. The equatorial surface velocity approaches 20% the speed of light. These millisecond pulsars challenge our understanding of how matter behaves under the most extreme conditions nature can produce. Sometimes pulsars exhibit peculiar sudden changes in their rotation rate, events called glitches. Without warning, a pulsar will speed up, increasing its spin rate by a tiny but measurable amount before gradually relaxing back toward its previous behavior. These glitches are thought to arise from the star's interior structure, where superfluids, fluids that flow without any friction whatsoever, may exist in layers below the solid crust. In a superfluid, quantum mechanics dominates even on macroscopic scales. The superfluid doesn't rotate like normal matter. Instead, its rotation is organized into quantized vortices, tiny whirlpools of circulation arranged in a lattice throughout the fluid. As the neutron star gradually slows due to energy loss through radiation, these vortices adjust in discrete steps. Occasionally, a large readjustment occurs, transferring angular momentum from the superfluid interior to the solid crust in what we observe as a glitch. Recent studies of the Vela pulsar, monitored continuously for years through early 2025, have revealed not just glitches, but subtle oscillations in the pulsar's spin-down rate that may be caused by the bending and unbending of these quantum vortices. It's a stunning example of quantum mechanics manifesting on the scale of objects more massive than the Sun. Quantum effects we can observe from hundreds of light years away. Researchers have also proposed that these glitching pulsars might emit gravitational waves, ripples in spacetime itself. When a pulsar glitches, the sudden rearrangement of matter inside could create disturbances powerful enough to send gravitational waves propagating across the cosmos. These would be far weaker than the waves produced by colliding black holes, but detecting them would give us an unprecedented window into the exotic physics occurring inside neutron stars. But neutron stars represent only one possible endpoint for stellar evolution. Push them just a bit more massive, add enough matter that even neutron degeneracy pressure cannot resist gravity's crush, and something even stranger happens. The star collapses beyond the neutron star stage, compressing without limit until it forms what we call a black hole, a region of space-time where gravity is so intense that not even light can escape. The boundary of a black hole is called the event horizon. It's not a physical surface you could touch, but rather a mathematical boundary in space-time that marks the point of no return. Cross the event horizon and you enter a realm where all paths through space-time lead inexorably inward, toward the center. The concept of escape loses all meaning. Even if you could somehow travel faster than light, you would still fall toward the singularity at the black hole's heart. That singularity is perhaps the greatest mystery in astrophysics. According to Einstein's general relativity, all the black hole's mass collapses to a point of zero volume and infinite density. It's a place where our physical theories break down completely, where the mathematics produces infinities and our equations become meaningless. Most physicists believe the singularity represents not a true physical reality, but rather a signpost indicating where general relativity fails and a theory of quantum gravity is needed. Some theoretical work suggests singularities might not exist at all. Perhaps quantum effects prevent the complete collapse, leaving instead some kind of ultra-dense core described by physics we don't yet understand. Proposals for what might replace the singularity include Planck stars, where spacetime itself becomes granular at the smaller scales, or fuzzballs from string theory, where the singularity is replaced by a tangled ball of vibrating strings and brains. One research team even explored gravistar models, hypothetical objects filled with dark energy instead of a singularity, and found they would appear nearly identical to classical black holes from the outside, producing similar shadows and gravitational effects. Roy Kerr, the physicist who discovered the mathematical solution for rotating black holes back in 1963, has recently argued that singularities shouldn't physically exist at all, that they're artifacts of pushing our equations beyond their valid regime. What we do know is that black holes exist. We've now directly imaged two of them, the supermassive black holes at the centers of the galaxy M87 and our own Milky Way, Sagittarius A star. The Event Horizon Telescope, a planet-sized array of radio dishes working together, captured the distinctive shadow cast by these black holes against the glowing gas swirling around them. The images show a dark region surrounded by a ring of light, precisely matching the predictions of general relativity. We've also detected gravitational waves from black holes colliding and merging. These ripples in spacetime, predicted by Einstein over a century ago, were first directly detected by the LIGO Observatory in 2015, when two black holes, each around 30 times the mass of the Sun, spiraled together and merged. The signal lasted only a fraction of a second, but in that brief moment we heard space-time itself ringing like a bell, the entire fabric of reality vibrating from the violence of the collision. Since that first detection, we've observed dozens of such mergers, including some between neutron stars, revealing a new way to observe the universe. Just as telescopes let us see cosmic objects through light, gravitational wave detectors let us hear space-time vibrations. We're learning that black holes come in a wider range of masses than expected, including some intermediate mass black holes, objects between stellar mass black holes and the supermassive monsters at galaxy centers, that challenge our understanding of how black holes form and grow. One of the strangest discoveries involves black holes found by the James Webb Space Telescope in the early universe. These ancient black holes, observed as they were more than 13 billion years ago, are far more massive than theoretical models predicted they should be at such young ages. Some contain millions or even billions of solar masses despite existing when the universe was less than 5% of its current age. They seem to have grown too massive too quickly, suggesting something wrong with our understanding of either black formation or growth, or perhaps both. Recent research even suggests that black holes themselves might contribute to dark energy. The idea is that matter falling into a black hole doesn't simply vanish, but rather becomes a form of vacuum energy, gradually leaking back out into the universe and contributing to cosmic expansion. It's a speculative idea, but measurements of black hole masses over cosmic time hint at a correlation between the growth of black holes and the accelerating expansion of the universe. Perhaps the most mind-bending aspect of black holes involves what happens to information that falls in. According to quantum mechanics, information cannot be destroyed. The quantum state of a system must always be preserved. But if something falls into a black hole and crosses the event horizon, that information seems to be lost forever, creating a paradox. Stephen Hawking spent much of his later career wrestling with this problem, eventually proposing that black holes slowly evaporate through a quantum process, and that information might be preserved in subtle correlations in the radiation they emit. The resolution to this information paradox, if there is one, will likely require a complete theory of quantum gravity. It points to a fundamental tension between our two best theories of physics: general relativity, which describes black holes and space-time curvature, and quantum mechanics, which insists on information preservation. Somewhere in the heart of a black hole, these theories meet and conflict, and reality itself remains ambiguous. And so we return again to mystery. These collapsed stars, these twisted regions of space-time, represent endpoints of stellar evolution, but also frontiers of knowledge. They show us matter behaving in ways we can barely comprehend, gravity powerful enough to trap even light, densities that approach the ultimate limits allowed by physics. They reveal the universe to be stranger and more extreme than our everyday experience could ever suggest. When you look up at the night sky, remember that scattered among those points of light are objects so bizarre that learning about them sounds like science fiction. Yet they're real as the earth beneath your feet. The universe has created wonders that stretch our imagination and challenge our understanding. And there, in the gap between what we can observe and what we can explain, lie some of the deepest mysteries existence has to offer. Signals from the depths. On the evening of August 15th, 1977, at Ohio State University's Big Ear Radio Telescope, a remarkable signal arrived from space. For 72 seconds, the telescope recorded radio waves at precisely the frequency where neutral hydrogen naturally emits, at an intensity 30 times stronger than the background noise of the universe. An astronomer reviewing the computer printout the next day was so startled that he circled the signal and wrote in the margin a single word: "Wow." Nearly 50 years later, we still don't know for certain what caused the wow signal. It came from the direction of the constellation Sagittarius, from a region of space where no unusual stars or objects were known. Despite numerous follow-up searches over decades, the signal has never repeated. It appeared once, left its mark, and vanished into silence. The search for explanations has been fascinating. In 2017, one astronomer proposed the signal might have come from a comet, its hydrogen cloud excited by solar radiation. But this explanation was contested by other researchers who argued comets don't produce emissions at the right frequency. More recently, in 2024, a team analyzing data from the Arecibo Observatory before its collapse identified similar but weaker signals coming from cold hydrogen clouds suddenly illuminated by intense bursts of radiation from magnetars, neutron stars with magnetic fields 1,000 trillion times stronger than Earth's. According to this explanation, a rare and powerful flare from a magnetar, perhaps located behind or within the hydrogen cloud, energized the cloud's hydrogen atoms, causing them to emit an unusually intense burst of radio waves at exactly the frequency the Big Ear was monitoring. It would have been an exquisitely rare alignment of circumstances, the magnetar flaring at just the right moment, the cloud positioned just right, Earth's rotation bringing the Big Ear into alignment for precisely the duration needed to capture the signal. Whether this solves the mystery remains debated. Some researchers find the magnetar hypothesis compelling. Others note that several aspects of the wow signal don't quite match what such a scenario would produce. The signal remains, at best, only partially explained. A 72-second message from the cosmos that has tantalized and frustrated scientists for half a century. The wow signal is just one of many mysterious cosmic signals that have puzzled astronomers. In recent years, a new class of phenomena called fast radio bursts has captured widespread attention. These are extremely brief pulses of radio energy, lasting only milliseconds, but releasing as much energy as the sun produces in several days. They arrive from cosmological distances, from galaxies billions of light years away, meaning the actual energy release must be staggeringly powerful. Most fast radio bursts are detected only once, making them nearly impossible to study in detail. But a few sources have been found that repeat, sending out bursts at irregular intervals. One such repeating source, catalogued as FRB 1102, has been traced to a dim dwarf galaxy 3 billion light years from Earth. 15 bursts from this source were detected in a single session by the Breakthrough Listen project, which searches for signs of intelligent life. What could cause such energetic, brief pulses? The leading explanations involve neutron stars, particularly magnetars. The intense magnetic fields of these objects can cause their crusts to suddenly crack and shift, like earthquakes on Earth but vastly more violent, releasing tremendous bursts of energy as magnetic field lines snap and reconnect. Alternatively, the bursts might come from young neutron stars still surrounded by supernova debris, their magnetospheres interacting with this material in ways that produce the observed emissions. But the mystery deepens with each new detection. Some fast radio bursts show complex structures with multiple subpulses and peculiar patterns in their frequency evolution. Others appear to come from relatively empty regions of space where no obvious source is visible, even with our most powerful telescopes. In a few cases, apparent fast radio bursts turned out to be interference from satellites or even microwave ovens. But the genuine cosmic signals remain, arriving without warning from across the universe, challenging our understanding of what processes in nature can produce them. Then there are the ultra-high energy cosmic rays, particles that arrive from space, carrying energies that seem to violate fundamental physics. Most cosmic rays are relatively low-energy particles, primarily protons accelerated by supernova shocks or other energetic phenomena. But occasionally, extremely rare particles arrive with energies exceeding 1, followed by 20 zeros in electron volts, more energy than a professional baseball pitcher imparts to a fastball, but concentrated in a single subatomic particle. These ultra-high energy cosmic rays pose a profound puzzle. They shouldn't be able to reach us. There's a theoretical limit called the GZK cutoff, named after physicists Greisen, Zatsepin, and Kuzmin, who predicted that cosmic rays above a certain energy would interact with the cosmic microwave background radiation and lose energy before they could travel far through space. Ultra-high energy cosmic rays shouldn't be able to travel more than about 100 million light years without dropping below the cutoff. Yet we detect them, and they seem to arrive from all directions in space. Where are they coming from? What natural accelerator could impart such incredible energies to individual particles? Active galactic nuclei, supermassive black holes at galaxy centers feeding on matter are one possibility. The decay of super heavy particles left over from the Big Bang is another. Some exotic theories even propose that these particles arrive from outside our observable universe, or that they're evidence of violations of Einstein's relativity at extreme energies. Not all mysterious signals are as dramatic. Some are simply puzzling in their regularity and origin. Radio astronomers have discovered several sources that pulse with clock-like precision at unusual intervals. One such source pulses exactly every 2 hours. Another emits bursts every 18 minutes. These periods are too long to be explained by pulsars as we understand them. Neutron stars spinning hundreds of times per second, not once every couple of hours. What could produce such signals? One possibility is that they come from white dwarfs in binary systems, the stellar remnants interacting with companion stars in ways that produce periodic bursts of emission. Recent research in early 2025 traced one of these mysterious repeating signals to exactly such a system. A white dwarf with an intense magnetic field interacting with a cool, low-mass companion star. The white dwarf's magnetic field accelerates charged particles from the companion, creating the observed bursts. But this explanation doesn't fit all such signals, and some may arise from phenomena we haven't yet imagined. The cosmos is full of such enigmas, signals that arrive unexpectedly, phenomena that don't quite fit our models, observations that hover in that uncomfortable zone between explainable and mysterious. Each one reminds us how much of the universe's behavior we still don't understand. How many processes may be occurring that we've never witnessed, creating signatures we don't know how to interpret. Perhaps the most tantalizing question behind all these mysterious signals is whether any of them might be artificial, messages or signatures from other intelligent civilizations. The WOWS signal arrived at a frequency that many scientists consider an ideal channel for interstellar communication. Fast radio bursts, with their immense energies and brief durations, could in principle be signs of advanced technology, perhaps directed energy systems used for propulsion or communication across cosmic distances. Most astronomers think natural explanations for these phenomena will eventually be found. The universe, after all, has proven endlessly creative in generating phenomena that initially seem inexplicable. Pulsars themselves, when first discovered in the 1960s, seemed so artificial in their precise regularity that astronomers half-seriously called them LGM-1 and LGM-2, little green men. The possibility of a beacon from an alien civilization was briefly considered before the natural explanation of rapidly rotating neutron stars became clear. But possibility isn't the same as impossibility. The universe is vast and ancient. If even a tiny fraction of the billions of planets that orbit within their stars' habitable zones gave rise to technological civilizations, the cosmos could be full of intelligences we've never detected. Perhaps some of these mysterious signals are artificial, messages crossing the light years, most of them passing unnoticed because we don't know how to recognize or decode them. Or perhaps we are alone, or functionally alone, the only technological civilization in our cosmic neighborhood, in which case, these mysterious signals represent something even more profound, the universe speaking to itself, matter and energy interacting according to laws we haven't fully grasped, creating wonders we cannot yet explain. Either possibility fills me with a strange mixture of emotions. If some of these signals do come from other minds gazing out at the same stars we see, what profound questions that raises about intelligence, consciousness, the destiny of life in the cosmos. And if they're all natural, all just physics we don't yet understand, what that tells us about how much mystery remains to be discovered, how the universe can still surprise us even after centuries of scientific investigation. The night sky continues to flash and pulse with signals, most of them recorded automatically by our telescopes and saved to vast databases, waiting for someone to notice a pattern, an anomaly, something that doesn't fit. Somewhere in that accumulated data might be evidence of phenomena we've never imagined, or perhaps even that message from elsewhere that we've been wondering about since we first looked up and realized the stars were suns like our own. Branching realities. Close your eyes for a moment and imagine yourself at a fork in a road. You must choose one path or the other. In the conventional view of reality, you make a choice, walk down one path, and the other path becomes merely hypothetical, a possibility that might have happened but didn't. The other version of you that would have walked the other path doesn't exist. There is only one you, one timeline, one reality. But according to one interpretation of quantum mechanics, arguably the simplest and most direct reading of the mathematical equations, both versions of you do exist. When you chose a path, the universe split. In one branch, you walked left. In another, you walked right. Both branches are equally real. Both versions of you continue their journeys, unaware of each other, each convinced they inhabit the only reality. This is the many worlds interpretation of quantum mechanics, and it proposes something that sounds like science fiction. The existence of a vast, perhaps infinite, collection of parallel universes, constantly branching and diverging with every quantum event. Every time a particle faces a choice, to decay or not decay, to go through one slit or another, to spin up or spin down, reality splits into multiple branches, each representing one possible outcome. The idea emerged from the work of physicist Hugh Everett in 1957. Everett was grappling with a fundamental problem in quantum mechanics, the measurement problem. Quantum particles exist in superpositions, being in multiple states simultaneously until they're measured or observed. At the moment of measurement, the superposition collapses into a single definite state. But what causes this collapse? What makes observation special? The mathematics of quantum mechanics describes the smooth evolution of superpositions, but it doesn't explain why or how collapse occurs. Everett proposed a radical solution. There is no collapse. The superposition continues to exist, fully real, but splits into multiple non-interacting branches. Before measurement, a particle spinning both up and down exists as one system. After measurement, it continues to spin both up and down, but in two different branches of reality that can no longer communicate. In one branch, you observe spin up. In another, you observe spin down. Both observations actually happen. Both yous are real. The immediate reaction to this idea is often disbelief. It seems absurdly extravagant. Every quantum event creating new universes, the number of branches would be staggering, growing exponentially with each passing instant as countless particles throughout the universe undergo quantum interactions. Your body contains more than one, followed by 25 zeros worth of atoms, each one constantly involved in quantum processes. The branching would be unimaginably rapid and vast. But Everett and his modern defenders argue this isn't as extravagant as it sounds. The mathematics of quantum mechanics already contains all these branches implicitly. The wave function, the equation that describes quantum systems, includes all possibilities. The many worlds. Interpretation simply takes the mathematics seriously, allowing all the branches that the equations describe to be real. In this view, the interpretation doesn't add anything to the physics. It just removes the arbitrary and poorly understood wave function collapse. Moreover, from the perspective of any individual observer, nothing changes. You still experience one definite outcome to each measurement, one deterministic chain of events. The branching is invisible to you because you can't communicate with the other branches. Each version of you exists in what feels like a single, well-defined universe, following apparently classical laws, unaware of the vast multiplicity of parallel existences. The many worlds interpretation makes some physicists uneasy. How do we explain probability in a framework where every possible outcome actually occurs? In the conventional interpretation, quantum mechanics gives us probabilities, a 60% chance of one outcome, a 40% chance of another. But if both outcomes happen in different branches, what does probability even mean? Physicists David Deutsch and David Wallace have developed sophisticated arguments suggesting that probability emerges naturally from the structure of the branching. The more measure or weight a particular branch has in the quantum wave function, the more likely you are to find yourself in that branch. It's a subtle argument, still debated among philosophers and physicists, but it shows that the many worlds interpretation can recover the probabilistic predictions of standard quantum mechanics. Another fascinating aspect involves quantum interference. In the famous double-slit experiment, individual particles seem to pass through two slits simultaneously, interfering with themselves to create a characteristic pattern. In the many worlds view, this makes perfect sense. The particle does go through both slits in different branches, and these branches temporarily interfere with each other quantum mechanically before decoherence separates them. The particle isn't interfering with itself, it's interfering with its alternate universe versions. This brings us to the concept of decoherence, which is crucial to understanding how the many worlds interpretation accounts for the apparent solidity and uniqueness of our classical experience. Decoherence is the process by which quantum superpositions become effectively classical through interaction with their environment. When a quantum system interacts with many environmental particles, air molecules, photons, thermal vibrations, information about the system's quantum state becomes distributed into the environment. The different branches of the superposition become entangled with different environmental states, making interference between branches effectively impossible. Recent simulations in 2024 have shown that when complex quantum systems undergo decoherence, they naturally organize into multiple distinct branches, each of which exhibits stable, classical-like behavior on large scales. This is remarkable. The emergence of our familiar classical world from quantum mechanics isn't something that needs to be imposed. It arises spontaneously from the many worlds framework when systems are sufficiently complex and interact with their environment. But the many worlds interpretation is just one way that the multiverse concept appears in physics. There are other types of multiverses arising from different considerations. Cosmological inflation, the rapid expansion of the early universe, naturally predicts what's called the level 1 multiverse, regions of space beyond our observable horizon that have the same physical laws but different arrangements of matter. Because the universe may be infinite or at least vastly larger than the observable portion, there could be an infinite number of such regions, many of them containing galaxies, stars, planets, even exact duplicates of ourselves, living out identical or slightly different lives. Then there's the level 2 multiverse, arising from eternal inflation. Different regions of the multiverse might undergo inflation at different times and in different ways, ending up with different values for physical constants, different types of fundamental particles, even different numbers of spatial dimensions. These bubble universes would be forever causally disconnected from ours, each one potentially having radically different physics. String theory, which attempts to unify quantum mechanics with gravity, predicts something called the landscape multiverse. String theory requires extra dimensions beyond the three spatial dimensions we experience. How these extra dimensions are configured, curled up in particular shapes, determines what the physical laws look like in the remaining dimensions. The number of possible configurations is enormous, perhaps one followed by 500 zeros, each corresponding to a universe with different physical properties. All these multiverse concepts share something in common. They're largely or entirely untestable by conventional scientific methods. We can't travel to other branches of the quantum wave function, can't see beyond our cosmic horizon, can't visit bubble universes formed in eternal inflation. This leads some scientists to dismiss multiverse ideas as unscientific speculation, metaphysics masquerading as physics. But others argue that we should take seriously whatever our best theories predict, even if those predictions involve unobservable entities. If quantum mechanics, applied consistently without arbitrary wave function collapse, implies multiple branches of reality, why should we reject those branches just because we can't see them? If inflation naturally predicts regions beyond our horizon, why should we assume they don't exist? There's something haunting about the possibility of parallel universes. Every decision you've ever made, every random event that has shaped your life might have gone differently in some other branch of reality. There might be versions of you who made different choices, followed different paths, became different people. An infinite variety of yous, each one convinced they're the only one, each one living out their particular version of existence in isolation from all the others. Or perhaps you're unique, the only you in all of existence, living in a single timeline, in a single universe. Perhaps when you make choices, alternatives really do disappear, possibilities collapsing into the single actuality of what happens. Perhaps the vastness of the cosmos is still bounded, still finite, still containing just this one coherent reality. We don't know. And that uncertainty itself is part of the mystery, not knowing whether we inhabit one universe or countless, whether our reality is all that exists or merely one thread in an incomprehensibly vast web of parallel existences. The question touches on fundamental issues of identity and meaning. Does it matter if other versions of you exist elsewhere? Does uniqueness require being alone in reality, or can you be unique even in a multiverse? These are questions that physics alone cannot answer. They require philosophy, introspection, perhaps a willingness to sit with uncertainty. The mathematics can tell us what's possible, what's consistent with our observations and our theories. But meaning, significance, the felt quality of existence, these emerge from a different kind of inquiry. Still, there's something beautiful about the idea that reality might be far richer and stranger than a single timeline in a single universe. If the multiverse exists in any of its forms, then the totality of existence is almost incomprehensibly vast, containing every possible variation allowed by physical law, every story that could be told, every life that could be lived. Worlds in the habitable darkness, 48 light years from Earth, in the constellation Cetus, orbits a world that has captured the attention of astronomers searching for life beyond our solar system. This planet, designated LHS 1140b, is a super-Earth, larger and more massive than our own world, yet still rocky, circling a small red dwarf star much cooler and dimmer than our sun. What makes this planet extraordinary is not its size or composition, but rather what may lie upon its surface: liquid water. For years after its discovery, astronomers debated what kind of planet LHS 1140b might be. Was it a mini Neptune, an essentially gaseous world with no solid surface? Or was it truly a rocky super-Earth? And if rocky, what kind of atmosphere, if any, might it possess? In 2024, observations from the James Webb Space Telescope finally provided some answers. The data revealed that LHS 1140b is likely not a gaseous mini-Neptune. Instead, it appears to be less dense than expected for a rocky planet, suggesting that 10 to 20% of its mass consists of water. This isn't water distributed throughout the planet's interior, but rather a vast ocean, possibly covered by an ice shell, existing on or near the surface. LHS 1140b may be a true water world, an ocean planet of a type that doesn't exist in our solar system. Because of the physics of tidal locking, the way that planets close to their stars end up with one face always pointed toward the star, LHS 1140b likely keeps the same hemisphere, perpetually facing its sun. This creates extreme conditions. The day side would be relatively warm, while the night side would be frozen. But at the substellar point, the spot on the planet that always faces the star, conditions might be temperate enough for liquid water to exist, perhaps as an open ocean surrounded by ice, like a cosmic eye gazing at its star. This discovery represents more than just finding another interesting exoplanet. It demonstrates that the James Webb Space Telescope can detect and characterize atmospheres around potentially habitable worlds, bringing us closer to answering one of humanity's most profound questions. Are we alone in the universe? Since the first confirmed detection of an exoplanet orbiting a sun-like star in 1995, astronomers have discovered thousands of worlds beyond our solar system. As of late 2025, the confirmed count stands above 6,000, with thousands more candidates awaiting verification. These planets span a bewildering range. Hot Jupiters orbiting closer to their stars than Mercury orbits our Sun, reaching surface temperatures high enough to vaporize rock, ice giants similar to Neptune and Uranus, rocky worlds smaller than Earth, and super-Earths, a class of planet common in the galaxy yet absent from our own solar system. The James Webb Space Telescope has revolutionized our ability to study these distant worlds. Unlike previous instruments that could mainly detect exoplanets indirectly, watching for the dimming of starlight as a planet passes in front of its star, or measuring the wobble in a star's motion caused by an orbiting planet's gravity, JWST can analyze the actual light that passes through planetary atmospheres or reflects off planetary surfaces. When a planet transits in front of its star, some starlight filters through the planet's atmosphere before reaching us. Different molecules in the atmosphere absorb light at specific wavelengths, creating a chemical fingerprint. JWST's infrared sensitivity allows it to detect these fingerprints with unprecedented clarity, identifying specific gases, water vapor, carbon dioxide, methane, sulfur dioxide, and potentially even more complex molecules that might hint at biological activity. One particularly interesting exoplanet is K2-18b, another super-Earth orbiting in its star's habitable zone, about 124 light-years from Earth. JWST observations in 2023 detected both methane and carbon dioxide in its atmosphere, consistent with what's called a Hycean world, a hypothetical type of planet with a hydrogen-rich atmosphere over a global ocean of liquid water. Some researchers even claimed to detect dimethyl sulfide, a molecule that on Earth is primarily produced by living organisms, particularly marine phytoplankton. This potential detection of a biosignature immediately generated excitement and controversy. Other researchers analyzing the same data argued that the signal attributed to dimethyl sulfide might actually be methane at higher altitudes, or simply noise in the data. The debate continues, with more JWST observations planned to clarify the situation, but regardless of the outcome for K2-18b specifically, the controversy highlights how close we are to potentially detecting life on another world, close enough that we're arguing about specific molecules in specific planetary atmospheres, rather than speaking in abstract terms about what might someday be possible. The search for habitable worlds focuses primarily on planets in what's called the habitable zone, the range of distances from a star where temperatures allow liquid water to exist on a planet's surface. For stars like our Sun, this zone extends from roughly where Venus orbits to slightly beyond Mars. For smaller, cooler red dwarf stars, which are far more common in the galaxy, the habitable zone lies much closer to the star, meaning planets can orbit in days or weeks rather than months or years. Red dwarf stars present both opportunities and challenges for habitability. On one hand, they're extremely long-lived, burning steadily for trillions of years, rather than the billions of years that sun-like stars have. Life would have vastly more time to emerge and evolve on planets orbiting red dwarfs. On the other hand, red dwarfs are prone to powerful flares that could strip away planetary atmospheres, sterilizing their surfaces with intense radiation. The close orbits required to stay in the habitable zone might also lead to tidal locking, creating planets with permanent day and night sides that could make maintaining a stable climate difficult. Despite these challenges, red dwarfs remain prime targets in the search for habitable worlds, simply because they're so abundant. Perhaps 75% of all stars in our galaxy are red dwarfs. If even a small fraction of them host habitable planets, the galaxy could contain billions of worlds where life might exist. In 2025, JWST directly imaged an exoplanet for the first time. A significant achievement. The planet, orbiting a young star called 2WA7, about 111 light-years away, was spotted within a gap in the star's debris disk. Direct imaging of exoplanets is extraordinarily challenging because stars are so much brighter than their planets. JWST's sensitivity and its instruments that can block starlight allowed it to capture an image of this distant world, opening new possibilities for studying exoplanets without waiting for them to transit in front of their stars. Some of the most intriguing discoveries involve systems with multiple planets. The TRAPPIST-1 system, 40 light-years away, hosts 7 Earth-sized planets orbiting an ultra-cool red dwarf. 3 of these planets orbit in the habitable zone. JWST has begun characterizing their atmospheres, revealing that at least some of them likely lack the thick hydrogen atmospheres that would make them mini-Neptunes. This is crucial. It means these worlds are rocky and potentially capable of hosting life, rather than being gas balls with no solid surface. The Proxima Centauri system, our closest stellar neighbor at just 4.2 light-years away, is known to have at least 2 planets, possibly 3. One of them, Proxima Centauri b, orbits in the habitable zone with a mass similar to Earth's. Recent discoveries have identified additional planets in the Alpha Centauri system. These are literally our nearest neighbors, worlds we might someday visit with advanced spacecraft. The statistical analyses of exoplanet discoveries suggest something remarkable. Planetary systems are the rule, not the exception. Most stars have planets. Rocky planets in habitable zones are common. The Milky Way alone likely contains tens of billions of potentially habitable worlds. The universe as a whole, with its hundreds of billions of galaxies, might contain more habitable planets than there are grains of sand on all of Earth's beaches. Yet despite this abundance, we have not yet found definitive evidence of life elsewhere. This is the Fermi paradox, named after physicist Enrico Fermi, who asked, "Where is everybody? If life is common, if some fraction of life evolves intelligence, if some fraction of intelligence develops technology, then where are all the aliens? Why haven't we detected signals, observed engineering projects, encountered visitors?" Possible explanations range from the pessimistic to the optimistic. Perhaps life is actually rare, arising only under very specific circumstances that aren't as common as we think. Perhaps intelligence is rare, or technology is rare, or spacefaring civilizations inevitably destroy themselves before expanding across the stars. Perhaps civilizations exist but are quiet, deliberately avoiding broadcasts that might attract attention. Perhaps they exist in forms so alien we wouldn't recognize them, or communicate in ways we can't detect. Or perhaps we are alone, or nearly so. One of the first technological civilizations to arise in our region of the galaxy. In an infinite universe, even rare events must happen somewhere. Perhaps we exist in a rare pocket where the conditions for complex life converged, and the vast majority of those billions of worlds remain barren, their potential unrealized. The search continues. JBST will spend years observing exoplanet atmospheres, building a catalogue of their compositions, looking for combinations of gases that would be hard to explain without life. Oxygen and methane together, for instance, or other more exotic biosignatures proposed by astrobiologists. Future telescopes being planned, like the proposed Habitable Worlds Observatory, will have even greater capabilities, potentially able to take actual images of Earth-like planets around nearby stars and analyze their light for signs of oceans, continents, vegetation. Within a generation, we may have an answer to whether life exists elsewhere. We may detect clear biosignatures in an exoplanet's atmosphere, or we may comprehensively survey enough nearby habitable worlds to conclude that, at least in our cosmic neighborhood, life on Earth is unique. Either answer would be profound, reshaping our understanding of our place in the universe. As you drift towards sleep tonight, consider that above you, beyond the air and clouds, beyond the moon and planets of our solar system, spread across the galaxy, orbit countless worlds. Some circle red dwarf stars, tidally locked, with oceans on their day sides and ice on their night sides. Others orbit sun-like stars, at comfortable distances, enjoying regular cycles of day and night, perhaps with seasons, as their tilted axes carry them around their suns. Some may be water worlds with global oceans, others desert worlds with no rain for millennia. Still others, ice worlds where liquid water, if it exists at all, is buried beneath kilometers of frozen crust. A few of these worlds might harbor life, perhaps just simple microbes in subsurface oceans, perhaps complex ecosystems with photosynthetic organisms and multicellular creatures, perhaps, just maybe, intelligent beings, looking up at their own night skies and wondering, as we do, whether anyone else is out there pondering the same questions. The search for cosmic origins, beyond the questions of what fills the universe and what signals cross the void, there lies an even deeper mystery. How did all of this begin? Not just the moment of the Big Bang itself, but the conditions that made that beginning possible. Why does the universe exist at all? Why does it have the particular laws of physics it does? These questions push us to the very edge of what science can address, into territory where physics blends with philosophy, where mathematics touches on metaphysics. One of the most profound mysteries involves the fundamental constants of nature, numbers like the speed of light, the strength of gravity, the mass of the electron, the charge of a proton. These constants appear arbitrary. They could, in principle, have any value. Yet they have the precise values they do, and those values make our universe possible. If gravity were slightly stronger, stars would burn out too quickly for planets to form and life to evolve. If it were slightly weaker, stars might never ignite at all. If the electromagnetic force had a different strength, atoms as we know them couldn't exist. The universe seems fine-tuned for the existence of complexity, structure, and ultimately life. This observation has led to what's called the anthropic principle. In its weak form, it simply notes that we should not be surprised to find ourselves in a universe capable of producing observers, since we could only exist in such a universe. It's a selection effect. We necessarily observe a universe compatible with our existence, just as fish necessarily find themselves in water. But the strong anthropic principle goes further, suggesting that the universe must have properties that allow life to develop at some point in its history. Some physicists find this idea troubling. It seems to put observers at the center of physical explanation in a way that feels unscientific, even mystical. Others embrace it as a genuine insight into the nature of reality. If our universe is just one among many in a vast multiverse, each with different values for the fundamental constants, then we naturally find ourselves in one of the rare universes where those constants allow for complexity and life. The apparent fine-tuning isn't a cosmic coincidence requiring explanation. It's an inevitable consequence of observer selection in a multiverse. But this leads to another question. Where do the laws of physics themselves come from? In our universe, we have quantum mechanics and relativity, conservation laws, and symmetry principles. Other possible universes might have completely different laws, or perhaps no consistent laws at all. What determines which set of laws actually governs reality? Is there some deeper principle from which all possible physical laws emerge? String theory and its extensions have attempted to provide a framework for answering such questions. In string theory, the fundamental constituents of reality aren't point-like particles, but tiny vibrating strings. Different vibration patterns of these strings give rise to different particles, electrons, quarks, photons, and so on. The theory requires extra spatial dimensions beyond the three we experience, and how those dimensions are configured determines what the effective laws of physics look like in our observable three-dimensional world. This leads to the landscape problem. There may be an enormous number of possible ways to configure the extra dimensions, perhaps one followed by 500 zeros worth of different possibilities, each giving rise to a different effective universe with different physical laws and constants. If all these possibilities are somehow realized, we have a multiverse on a scale that dwarfs, even the quantum many-worlds or the inflationary bubble universes. We would need to explain not just why our universe has the laws it does, but why these particular laws manifested here while countless others manifested elsewhere. Some physicists have pursued a different approach, seeking a theory of everything that would uniquely determine the laws of physics through some principle of mathematical elegance or logical necessity. Perhaps there is only one mathematically consistent set of fundamental laws, and the universe we observe is the inevitable expression of that consistency. This dream goes back to Einstein, who spent the last decades of his life searching for a unified field theory that would bring together all the forces of nature into a single coherent framework. But the search for a theory of everything faces profound challenges. We don't yet have a working theory of quantum gravity, let alone a complete unification of all forces and particles. Even if we achieved such a theory, we would face the question of why that particular theory describes reality. Why do mathematical structures correspond to physical reality at all? The physicist Eugene Wigner called this the unreasonable effectiveness of mathematics in the natural sciences. The mysterious fact that abstract mathematical concepts turn out to describe the physical world with astonishing precision. Consider general relativity. Einstein developed the theory by thinking about the geometry of spacetime, using sophisticated mathematical tools from differential geometry. Yet when physicists tested the theory's predictions, the bending of starlight around the sun, the precession of Mercury's orbit, the existence of gravitational waves, nature matched the mathematics perfectly. Why should the universe care about human mathematics? Why should the abstract manipulations of symbols on paper correspond so precisely to how matter and energy actually behave? One radical answer is mathematical universe hypothesis, proposed by cosmologist Max Tegmark. Perhaps mathematics isn't just a description of reality. Perhaps it is reality. Every mathematically consistent structure exists in some sense, and our universe is simply one such structure, no more or less real than any other. We find ourselves in this particular mathematical structure because it's one that permits the existence of observers. Physical existence and mathematical existence are the same thing. This idea is deeply strange, and many physicists reject it as too speculative, but it illustrates how far into conceptual territory we're pushed when we seriously try to answer questions about cosmic origins. The mystery isn't just what happened in the first moments after the Big Bang, or even what caused the Big Bang. It's why anything exists at all, why existence takes the form it does, why the universe is comprehensible to us. These are questions that may never have definitive scientific answers. Science excels at explaining how things work, at making predictions and testing them against observations, but questions of ultimate origin and purpose push beyond the domain where empirical testing is possible. We can trace cosmic history back to the first tiny fractions of a second. We can infer what conditions must have been like even earlier, but we hit a wall where the laws of physics, as we understand them, break down. Some scientists argue that these questions are therefore meaningless or unanswerable. Others maintain that while science may not be able to fully resolve them, they remain valid and important questions that hint at deeper aspects of reality we haven't yet grasped. The universe exists. It has specific properties and laws. Those facts demand some kind of explanation, even if we may never fully satisfy our curiosity about them. The cosmic horizon. There's a particular poignancy to cosmic mysteries when we recognize that some questions may be unanswerable, not because of limitations in our theories, but because of fundamental limits imposed by the structure of the universe itself. The speed of light is finite. The universe has a finite age. These facts combine to create what's called the cosmic horizon, a boundary beyond which we cannot see, no matter how good our telescopes become. Light from the most distant observable galaxies has been traveling toward us for over 13 billion years, having been emitted when the universe was very young. But there are surely regions of space even farther away, from which light has not yet had time to reach us. These regions are as real as the galaxies we can see, but they lie beyond our cosmic horizon. We can never observe them directly, never know what they contain, never receive any signal or influence from them. As the universe continues to expand, driven by dark energy, this horizon isn't static. Regions that are currently observable will eventually recede beyond the horizon, as space expands faster than light can traverse it. In the far future, as we discussed earlier, observers in our local group of galaxies will see a universe much emptier than we do. Most galaxies will have disappeared beyond the horizon. The cosmic microwave background will have cooled to imperceptibility. Future scientists will lack the evidence we have today for the Big Bang and cosmic expansion. This raises an unsettling possibility. Perhaps we too are missing crucial evidence about the nature of the universe. Perhaps there are phenomena, structures, or events that occurred beyond our cosmic horizon that profoundly shaped the universe we inhabit, but can never be directly observed. We might develop theories that work perfectly well for the observable universe while missing crucial pieces of the larger cosmic puzzle. For instance, what if the conditions that led to the Big Bang were not uniform throughout all of existence? What if our observable universe is just one region in a much larger cosmic structure that underwent inflation, while other regions evolved differently? What if there are processes occurring at scales larger than our horizon that fundamentally influence the physics we observe, but in ways we can never directly detect? This is related to another profound limitation, the quantum mechanical uncertainty principle. At the most fundamental level, there are limits to what we can know simultaneously about conjugate quantities like position and momentum, energy and time. These aren't just practical limitations of measurement, but fundamental features of reality. The universe itself doesn't have definite values for these quantities beyond what the uncertainty principle allows. This quantum uncertainty was magnified during cosmic inflation, when microscopic quantum fluctuations were stretched to macroscopic and even cosmic scales. The positions and properties of galaxies today ultimately trace back to quantum uncertainties in the earliest moments of the universe. There's an irreducible randomness built into the cosmic structure, a fundamental unpredictability that no amount of improved measurement or theory can eliminate. We must come to terms with this. There will always be mysteries, not because we're not smart enough or our instruments aren't sensitive enough, but because the universe itself contains genuine randomness, genuine horizons beyond which we cannot see, genuine questions that have no definite answers. This isn't a failure of science, but rather a feature of reality that science has discovered. And yet, knowing this doesn't diminish the value of the search. Every mystery we solve, even if it reveals deeper mysteries beyond, represents genuine progress in understanding. Every observation we make, every theory we develop, every connection we draw between seemingly disparate phenomena adds to the web of knowledge we've constructed. We may never have complete answers, but the partial answers we have represent real achievements, genuine insights into the nature of existence. Consciousness and cosmos. There's one more mystery we should consider, perhaps the deepest of all: consciousness itself. You are aware of these words. You have subjective experiences, thoughts, feelings, a sense of self. This inner mental life is as real to you as the external physical world, yet it remains profoundly mysterious. How it arises from the physical processes in your brain. This is called the hard problem of consciousness. We can study the neural correlates of consciousness, mapping which brain regions are active during different mental states. We can investigate how information is processed in neural networks, how sensory inputs are transformed into perceptions and actions. But none of this explains why there is something it's like to be you, why physical processes in your brain give rise to subjective experience. Some philosophers and scientists argue that consciousness is simply what complex information processing feels like from the inside. When a system reaches sufficient complexity and integrates information in the right ways, experience emerges. Others maintain that this still doesn't bridge the explanatory gap between objective physical processes and subjective experience. Still others suggest that consciousness might be more fundamental than we think, perhaps a basic feature of the universe like space and time, rather than something that emerges only in complex brains. Why raise this question in an exploration of cosmic mysteries? Because consciousness might be related to some of the puzzles we've encountered. The measurement problem in quantum mechanics involves observation. The transition from quantum superposition to definite outcomes seems to require an observer. What constitutes an observer? Does consciousness play a role in collapsing the wave function? Or is this role played by any interaction that creates decoherence, regardless of consciousness? The strong anthropic principle suggests that observer-dependent selection effects may explain why the universe has the properties it does, but this requires observers to exist. What is special about observers? Is it just that they can form theories and ask questions, or is there something about consciousness itself that's fundamentally connected to the nature of reality? These are deeply speculative questions, and many scientists prefer to avoid them, focusing on problems that can be more clearly defined and investigated. But they hover at the edges of cosmology and quantum mechanics, hinting at connections we don't yet understand between mind and universe, observer and observed, consciousness and reality. Consider too that consciousness arose in the universe. Through billions of years of cosmic and biological evolution, matter organized itself into forms capable of self-awareness. The universe created beings that can contemplate the universe. This is remarkable. For most of cosmic history, there was presumably no consciousness anywhere, just matter and energy evolving according to physical law. Then, on at least one planet, possibly many, this unconscious universe gave birth to consciousness. We are the universe become aware of itself, and this self-awareness allows us to pose questions about cosmic origins and destiny, about the nature of reality and existence. Perhaps consciousness is not just an accidental byproduct of complex chemistry, but something more significant, a way the universe explores its own possibilities, reflects on its own nature, creates meaning in a cosmos that otherwise simply is. Or perhaps we're dramatically overestimating our importance. Perhaps consciousness is just what certain physical systems do, no more cosmically significant than the way crystals form or planets orbit. The universe doesn't care that we exist, doesn't notice our observations, doesn't derive meaning from our meaning making. We're brief fluctuations of organization in a vast sea of entropy, our thoughts and feelings as ephemeral as clouds, leaving no lasting mark on the cosmos. Either way, whether consciousness is cosmically significant or merely incidental, the fact remains that you experience this moment. You ponder these mysteries. You feel wonder and curiosity, and that experience, whatever its ultimate nature and significance, is the lens through which you encounter everything else. The mysteries of the universe are mysteries to you because you are conscious, because you can ask questions, because you care about answers. This brings us full circle to where we began: the universe as mystery, as an object of wonder, as something that exceeds our complete understanding, yet invites our ongoing exploration. We've journeyed through dark matter and dark energy, through cosmic origins and collapsed stars, through signals and multiverses and distant worlds. We've encountered limits to our knowledge, horizons we cannot cross, uncertainties we cannot eliminate, questions we may never fully answer. The weight of wonder. We have journeyed far tonight, through dark matter and dark energy, through the first light of creation preserved in the cosmic microwave background, through the extreme physics of collapsed stars and gravitational waves, through mysterious signals and possible parallel universes, to worlds orbiting other suns where water might flow and life might dwell. And now, as our exploration draws toward its close, it's worth pausing to consider what all these mysteries mean, what they tell us about ourselves and the universe we inhabit. The cosmos, as we've seen, is vastly stranger than our everyday experience suggests. The solid, predictable world of human-scale objects, chairs and tables, rocks and trees, the ground beneath our feet, emerges from a substrate of quantum weirdness, where particles exist in multiple states until observed, where the very notion of a particle as a discrete localized object breaks down. The universe is built on foundations that violate common sense, that challenge our intuitions, that require mathematical abstractions to even describe. And yet, out of this quantum strangeness emerges the classical world we know. Atoms combine into molecules, molecules into structures, structures into living things into consciousness, into minds capable of pondering their own origins, of detecting photons that have traveled for billions of years, of conceiving of realities beyond what any human can directly experience. We stand at a peculiar moment in cosmic history. The universe is about 13.8 billion years old. The first stars formed when the universe was just a few 100 million years old. Our sun, a latecomer, formed only 4.5 billion years ago. Life on Earth arose quickly after the planet cooled, but complex life took billions of years to emerge, and technological civilization is measured in thousands of years. We exist now, in this particular epoch, when the universe is old enough to have created the elements necessary for life. When stars still burn brightly in the night sky, when the cosmic microwave background is still detectable, when the expansion of space hasn't yet carried all distant galaxies beyond our ability to observe them. In the deep future, trillions of years from now, if the current cosmological model holds, things will look very different. Most stars will have exhausted their fuel and faded to darkness. The universe will have expanded so much that galaxies outside our local group will be receding faster than light, invisible to any observer. Even the cosmic microwave background will have cooled and redshifted to imperceptibility. Any civilizations arising in that far future would lack many of the clues we have used to piece together cosmic history. We are fortunate, in a sense, to live when we do. The universe is still young enough, still bright enough, still observable enough that we can piece together its history and structure. We can see the light from the cosmic dawn, Detect the gravitational waves from colliding black holes billions of light years away. Study the atmospheres of planets orbiting other stars. We live in an age of cosmic revelation, when one mystery after another yields to our instruments and our theories, even as each answer reveals deeper mysteries beyond. The mysteries we've explored tonight: dark matter and dark energy, the meaning of quantum mechanics, the nature of singularities, the possibility of parallel universes, the question of life elsewhere. These are not failures of science, but rather its frontier. They mark the boundary between the known and unknown, between the comfortable familiarity of established knowledge and the discomfort of genuine uncertainty. They remind us that for all we've learned, for all the progress humanity has made in understanding the cosmos, we remain at the very beginning of a much longer journey. Perhaps some of these mysteries will be solved in your lifetime. Perhaps researchers will discover what dark matter is made of, will develop a working theory of quantum gravity, will detect unmistakable biosignatures in an exoplanet's atmosphere. Perhaps other mysteries will deepen, branching into new questions we haven't yet thought to ask. This is how science works, not as a steady march toward complete knowledge, but as an ongoing conversation between theories and observations, between predictions and surprises, between what we think we understand and what the universe actually does. What draws me back again and again to these cosmic mysteries is how they place human concerns in perspective without making them meaningless. Yes, we are tiny. Our entire planet could fit 1,000,000 times over inside our sun. Our sun is an average star among hundreds of billions in our galaxy. Our galaxy is one among hundreds of billions we can observe. The scales of space and time in the universe make human life seem like the briefest flicker, here and gone in an instant against the backdrop of cosmic eternity. And yet we are the universe becoming aware of itself. We are matter that has organized itself sufficiently to contemplate its own nature, to ask where it came from and where it's going, to feel awe at the beauty of a spiral galaxy or the mathematical elegance of Einstein's equations. Every thought you think, every emotion you feel, every dream you dream represents something genuinely new in the universe: consciousness, subjectivity, experience emerging from the intricate dance of atoms and molecules that make up your brain. The mysteries of the universe are, in a very real sense, mysteries about ourselves. We are made of atoms forged in stellar cores, organized according to quantum mechanical laws, existing in a universe shaped by dark matter and dark energy, perhaps one universe among many, living on a world that circles a star not so different from the billions of other stars that might host their own living worlds. To understand the universe is to understand the context of our own existence, the cosmic stage on which the drama of human life unfolds. As you prepare to drift into sleep, carry with you this sense of wonder and mystery. You are a pattern of matter that has existed for a few decades on a world that has orbited its star for billions of years, in a galaxy that has wheeled through space for billions of years more, in a universe that began in a moment of creation we can trace but not fully understand. You are temporary and you are eternal, insignificant and profound. A fleeting arrangement of particles and a portal through which the universe observes itself. The mysteries we've explored tonight, the invisible matter holding galaxies together, the ancient light from cosmic dawn, the collapsed stars warping space-time, the enigmatic signals from deep space, the possible parallel worlds branching with each quantum event, the distant planets that might harbor life. These are not separate from you, but intimately connected to your existence. You live within these mysteries, are shaped by them, are in your deepest nature made of the same substance that composes the entire cosmos. Let that awareness settle over you now. Feel the weight of it, but also the lightness, the understanding that you are part of something vast and strange and beautiful beyond description. The universe has spent billions of years creating you, arranging its matter in precise configurations, allowing complexity to emerge from simplicity, consciousness from unconsciousness, wonder from mere physical law. And here you are. Here we all are. Temporary patterns in the cosmic flow, briefly aware, briefly capable of asking why and how and what comes next. We peer out at the mysteries surrounding us and we wonder. And in that wondering, in that questioning, in that refusal to accept easy answers, we embody something precious, the universe's capacity to know itself, to marvel at itself, to appreciate the profound strangeness of existence. Sleep well, dear listener. Dream of dark matter halos and colliding black holes, of radio signals crossing the light years, of parallel worlds where different versions of your story unfold. Dream of planets orbiting distant suns beneath alien skies, of the first light from creation still echoing through space, of mysteries we've solved and mysteries we've yet to discover. And know that when you wake, the universe will still be here, vast and mysterious and filled with wonders waiting to be found. The search continues, the questions remain, and we are fortunate beyond measure to live in a cosmos strange and beautiful enough to inspire such profound wonder. If you enjoyed this journey through the mysteries of the universe, please like this video and subscribe to Dreamlab Knowledge for more explorations into the fascinating territories of science, space, and cosmic understanding. Thank you for pondering these profound questions with us tonight. Until next time, sleep peacefully, dream deeply, and never stop wondering at the magnificent mystery of existence itself.